Hi, welcome to another Build With Me project. This is a simple RGB LED display kit that's available from Banggood and probably from many other sellers as well. Sadly, it comes with no instructions and the details on the website are not that great. But actually, don't let that put you off. It's quite an easy and simple kit to put together, and if you follow through with this video you'll see just how easy it is. There's very few components, quite simple soldering, an ideal project for those who are relatively new to electronics or somebody who just wants a nice nightlight type display to be able to put somewhere. So let's see what we've got in the package. A circuit board and a little bag of components. We've got a little battery box with a switch, a light dependent resistor, some standard resistors, microcontroller, and 10 LEDs. And no instructions. That's great. After taking a little time with this, looking at the circuit board, I managed to reverse engineer it. Not made easy by the fact that it's all in this matte black silk screen. Our solder resist always makes it a challenge tracing things out, but it's a fairly simple circuit which I've got here. Let me just clear this off to one side. We can take a closer look at this. Now, even though there's no instructions, there are some pictures on Banggood's product page which I was able to zoom in on and just about make out the values of the resistors. We see on our circuit board we've got positions R1, R2, R3, R4. Now R1, 2 and 3 are all the same, 100 ohms resistors. But R4 is different. It's a 10k resistor. And helpfully they've given you one extra of each value. There's no decoupling capacitor on the microcontroller, so we'll see how reliable that proves to be, but it obviously must work. There's also no indication on the board as to which of these is positive and which of these is negative. I think positive is this lead, but I'll have to buzz that out and check that. And then I'll put up an image with superimposed onto this as to what each of those pins or values of resistors are, just to make it a bit easier for anybody who might be building this. But it's quite a nice circuit board, reasonably thick. So all of these RGB LEDs, these are numbered, 1 being here on the most left hand side, 2, 3, 4, 5, 6, 7, 8, 9, 10. The LEDs themselves, they've got one long pin, and that's denoting the common cathode. And on the board, I'll show a close-up of this. On the board we've got a square pad at each of the locations. That's indicating the cathode. And because there's only one way to put them around with the long lead into the square, it's sort of self-aligning for the LEDs. But as you can see, all of these LEDs have their every red LED's anode is connected together, and every blue is connected together, and every green is connected together, and then linked via the 100 ohm current limiting resistor to the microcontroller. Then it's the way it works is that the microcontroller multiplexes by alternately switching the anode or cathodes, obviously to ground, as each one is being addressed. Done at such a high frequency that the human eye can't see any flicker. It's just able to control things that way. Then the light dependent resistor, which I'm led to believe will affect what program is running on the microcontroller, will affect the program that is running. And then to change program, you simply interrupt the power supply, switch off and on in a rapid fashion to be able to select different programs. That seems to be what the operation is, just based on the video that's on the product page there on the Banggood website. So this is a close-up of the circuit board. This is the top of the circuit board, and as you can see, for the LEDs, one of the pins is denoted by a square, and that's the common cathode. So I'll just give you a view of this circuit board up close. As you can see, the matte black solder resist really can make things a bit tricky. To try and reverse engineer. So R4, that's the one that's 10K, that's the one that's different. The other three are 100 ohms. And this is the back of the board. It would have been nice if they'd given an indication as to the power input polarity. That's power input is these two, that one and this one over here. It would be nice if they'd put something on the silk screen just to identify which one's which, just to make things a bit easier, because there's no protection. If you connect the power up the wrong way around, you will do damage to the microcontroller. A little bit of damage to the solder mask there. This is a close-up on the leads of the RGB LEDs. As you can see, we've got one lead that's longer than the others, and that's denoting the common cathode for each of the three LEDs. And so as you can see, you can only put it in the one way round with having the long lead put into the hole with the square pad. If you turn the LED the other way up, it's obviously not in the right orientation. This is the microcontroller. I'm not sure exactly what this is. If I can find a data sheet, I'll link it in below and put it up on the screen what it is. In case you're wondering what it is, that is it. It just comes shoved into some polystyrene. There's no anti-static protection on this, so I presume it's reasonably robust. And that's just a little LDR, light dependent resistor, that is used to bring some modification to whatever program is running on this. So let's set about putting this together. Now, I've already checked with my multimeter the resistance of these two values and written them on here, 100 ohms and 10K, just so I don't get them mixed up. But we'll start with 100 ohms resistors. Just get 3 of those. And roughly form them into the shape they need. So these 100 ohm resistors, these are for current limiting on the LEDs, and they're just for positions R1, R2 and R3. R4, that's the 10K resistor, which we'll put in as well. It's as easy to do them all at once. And that's the 4 resistors soldered in. As usual, we always start with the lowest in height component and then work our way up. So I think the next component after this is going to be the microcontroller, and we'll put that in and carefully solder that up as there's no socket. So let's put the old microcontroller in, making sure that we observe pin 1 with the dot and also the notch at the top of the package. Yeah, there we go. So we're able to see that we've got it in the right place. The notch and also the dot signifying pin 1 is here on pin 1, and of course you can just see on the silk screen the legend for the notch. Because we've not got a socket for this integrated circuit, we just have to be careful when soldering it that we don't apply too much heat and do damage, because removing this will not be particularly easy. So we shall solder one pin up first. Then just flip it over and make sure that we're sat down to the board as much as possible, which we are. It's always worth checking. So what I like to do if I'm doing soldering integrated circuits directly to a board is not to go 1, 2, 3, 4, 5, 6 and solder them all in a row, but in order to just spread the heat so it's not all concentrated in one spot, I like to alternate and just do one pin at a time, starting in the corners and working inwards. Obviously whenever you get to the center you may have to just pause for a few seconds in between each joint just to allow things to cool and for that heat to dissipate. There is a little bit of an art to doing this. But if you're able to practice on some other components, you get into the way of being able to solder quite quickly without introducing a lot of heat into the part that you're soldering. They look good. So now it's going to be our little LDR. It doesn't matter which way round this goes. There is no polarity. And you could have it bent upwards. I'm just going to leave it kind of flat on the board. I'm actually going to let it come out a little bit so it's about the same height as the integrated circuit. There's way too much solder on that. So now it's on to just inserting the LEDs. So as you can see, we have one pin that is longer. That goes to the square hole in PCB. So this is a bit of a closer up view. And as you can see, we've got this aligned the right way around so that we can pop this in I just need to spread these leads ever so slightly. To be able to fit a bit better. So these won't go all the way in. As you can see, they're not quite perfectly aligning with the holes, but they will go down to those little square crimped bits on the LED, and actually those can just jam in there. That's the first one in place. I guess it's just lather, rinse, repeat. So when I've got a multiple of ones to solder up like this, I just solder up one lead on each one. Firstly, to be able to check that I've got them in the right spacing or positioning. But then also to be able to spread the heat from soldering so that it's not all concentrated and it has time to dissipate. Just a little bit easier if you splay them out ever so slightly. And it's always a good idea just to check your joints up close in case we've got any shorts or solder bridges. All looking good there. So now it's on to the battery pack. That's the last thing to get connected. I'm just going to tack this on, but first of all I need to know the polarity of this as to which lead is which. They're very, very similar. There's a very slight stripe on one lead, but I'm not very confident about positively identifying that, so I'm just going to get a couple of batteries to put in this, and then we can test this out with the multimeter. So I've got some rechargeable batteries with a questionable amount of charge in them, but they'll do. Running out of room here. Here's the meter. And switch that battery to on. And we managed to get it bingo first time. So we shall get some form of identification to mark these. You can see the very slight on the negative lead, the little dash. That is that. Because if we hook it up the other way around, as you can see, we've now got a little negative reading on our meter, showing polarity was the wrong way around, so that is negative. The dashed is negative. What I will do is I will just get a bit of tape and put a flag on the positive. My intention with this kit, let me just double check this, cut the brown for positive, that's correct. My intention with this kit is actually not to power it off this battery pack permanently. I will attach it just for testing purposes, as it's part of the kit, so that we're fully assembling the kit as it is. But I'm going to use one of my USB power banks, so I'll just hack an old USB lead and use that as power supply for this. Something I need to just double check is which of these two terminals is the positive. So I've got my meter in continuity mode. So let's just see. Pin 8 is supposed to be the ground. So this right hand one appears to be ground. Tin these leads and then we can just tack them on and we'll see if that is the case, or if we just send this whole thing up in smoke. Just get a bit of fresh solder on each of these. I'm not filling those holes with solder because it makes it awkward then to both remove and then put in a new. There we go. So now the moment of truth. Hey, we've got it right. Let's just turn off some of the lights. Now apparently if you just quickly switch on and off, it changes the mode. Yeah, covering that LDR slows down the program on that particular program. Well, I consider that a success. I'm going to hack a USB lead and put that onto it, and then I can measure what the current draw is on one of my USB meters, power meters. And then I've got a thought about encasing this. That'll probably be in a second part of the video, but give me a moment and we can hack together a USB lead onto this. So I've got myself just a little USB lead which I've peeled the ends off. Now, as you can see, very helpfully, if you look down here, very helpfully, both cores of this are very similar. One is like a very slight sort of aqua type colour, the other one's white. So I did the same thing as I did with the battery bank. I plugged it into a USB power bank and then measured using my multimeter as to which one was positive and which one was negative. So the one on this particular lead, the one that's slightly aqua coloured, is positive and the white is negative. But I've just put some black marker on there just to make it really clear so I don't completely mess up. So let's remove this battery bank, or this AA battery holder. I may well bring in the wires eventually from the back of this, but just for the moment I will feed it. Well, that would be helpful, wouldn't it? not stripped enough. Don't know why they put these two so far apart. Let's try that again. So now with our power bank, we can see how much this draws. 15 to 20 milliamps. And let's just turn this light off. It seems that the light sensor, the LDR, on most of these programs seems to just control the rate of change. So that's probably going to be it for this video. It's a bit messy, let's tidy this up. So that's probably it for this video. I am going to make another video where I make a little 3D printed case for this with a diffuser over the top. I think that'll just be make it quite nice and make it possible for it to just sit on a shelf somewhere looking pretty. I hope that this has been of some help, especially if you're trying to build this yourself. I will leave links for this, where I got this from Banggood, in the description, and I'll also leave a link to the schematic that I reverse engineered, so that makes it a bit easier for you. And I'll also put a picture up with labeling the resistor values and also which is positive and which is negative on the board. That'll all be linked to in the description below. But thank you for watching, and we'll see you the next time.